If you spend enough time looking at space news, you've probably seen the headlines. Stories telling you that somewhere out in the dark, a wandering planet, a rogue black hole, or a beam of pure radiation is on its way to instantly wipe out human civilization. It's easy to picture the cinematic nightmare, the Earth cracking open, turned into glowing debris in a matter of seconds by some invisible cosmic force. But this creates a practical problem for us. When we're trying to figure out where to actually spend planetary defense funding, we have to separate genuine, actionable threats from theoretical physics dressed up as anxiety-inducing clickbait. Because while the universe contains objects with an unimaginable capacity for destruction, raw power doesn't automatically translate into a mathematical risk to Earth. To audit these threats, we need to start with the baseline rule of astrophysics. Space is overwhelmingly, unfathomably empty. That emptiness is our primary shield.
This chart shows our cosmic threat matrix. We are mapping theoretical destructive impact on the vertical axis against the actual probability of Earth intersection on the horizontal axis. Pop science media loves to lump all these cosmic monsters, rogue planets, magnetars, gamma-ray bursts, and black holes right here in the top left. Maximum destruction, imminent arrival. But when we apply actual astrophysics, these data points shift drastically. The destructive capacity remains high, but the probability of intersection drops effectively to zero. By trading sensationalism for hard statistical reality, we stop looking at the cosmos as a ticking time bomb and start seeing it for what it actually is, a highly stable, predictable environment. This matrix breaks down the actual danger. We are going to score these anomalies by looking at the object, how we detect it, its effective kill radius, and the resulting risk score. Let's test our first category, the wanderers. Rogue planets are solitary bodies that were ejected from their solar systems, drifting blindly through the dark without a host star. We estimate there are billions of them out there. But to reach us, a rogue planet would have to cross a void so immense that the chance of it threading the needle to hit our solar system is statistically negligible. Then there are stellar mass black holes, the collapsed remnants of dead stars, known for extreme localized destruction. If you cross a black hole's event horizon, the gravity differential pulls on you so violently that you get stretched into a thin stream of atoms, a fatal mechanical process physicists call spaghettification. They emit no light, making them seem like perfect stealth predators. But modern astronomy spots them easily. We watch how their immense gravity bends background light and forces nearby stars into irregular orbits. Because interstellar space is vast and gravitational anomalies broadcast their presence across enormous distances, any wandering threat would be tracked by our telescopes decades, if not centuries, before it reached our local neighborhood. Our next category includes extreme phenomena that do not wander. They are permanently anchored in specific locations, starting with magnetars.
A magnetar is a dead star packing the strongest magnetic field in existence. Its effective kill radius is about 1,000 kilometers. Cross that line, and the magnetic pull will literally tear apart atomic structures in your body. That sounds alarming until you factor in our baseline rule of distance. There is absolutely zero evidence of any magnetar existing close enough to our solar system to pose a physical threat. The exact same logic applies to supermassive black holes. These are the structural anchors at the centers of galaxies, packing millions of solar masses into a single point. Our Milky Way has one named Sagittarius A star, but it is a fixed structural feature, sitting quietly 26,000 light-years away from our planet. The most violent gravitational and magnetic forces in existence are perfectly contained. They are rendered entirely harmless by the unfathomable scale of cosmic isolation. That leaves us with the ultimate remote threat, gamma-ray bursts, or GRBs, the highest energy explosions in the known universe. When a massive star collapses, it can release more energy in a few seconds than our sun will output over its entire 10 billion-year lifetime. But a GRB is not an expanding sphere of destruction. Physics dictates that the energy is concentrated into highly narrow, strictly directional beams. It acts like a razor-thin cosmic laser. For it to impact us, that beam would have to travel across thousands of light-years and intersect precisely with our tiny orbit. If a nearby beam were perfectly aligned with our coordinates, the radiation would indeed strip away Earth's protective ozone layer, leading to mass extinction. But this makes the deadliest weapon in the universe the equivalent of a blind sniper shot. The mathematical odds of a beam perfectly aligning with Earth's exact coordinates at this specific moment in time are functionally zero. This matrix shows our final audit. The risk scores for rogue planets, magnetars, supermassive black holes, and gamma-ray bursts all flatline at near zero. If we want a statistically relevant variable for planetary defense, we have to look in our own backyard, near-Earth asteroids. Unlike deep space anomalies, local solar system debris is tangible. It operates in our immediate vicinity, and more importantly, it is highly trackable and physically manageable. Applying rigorous math to the noise of deep space leaves us with a quiet conclusion. Earth is situated in an incredibly stable, secure pocket of the galaxy. So how should we process this information? Astrophysicists will absolutely keep studying these extreme cosmic objects to understand the mechanics of the universe. But as the public, we can confidently cross them off our list of existential worries. For actual planetary defense funding and science, our resources must be strictly dedicated to local, tangible targets where human intervention is viable. This requires moving past the dramatic cinematic narratives that grab our attention to embrace a drier but far more comforting statistical reality. The universe out there is violently fascinating, but your immediate, local solar system is the only place that actually demands your attention.